Thanks everyone for coming out tonight. So my name is Rob Zellem, and I work at NASA JPL, and I work on exoplanets. So basically what I do is I take all of your tax money and I use it to find aliens. So thank you for paying your taxes, appreciate it. So I'm an astronomer, like I said. This is a photo of me. No, that's actually not me. I'm not an astronaut. This is little Rob eons ago at the Kennedy Space Center, meeting my obvious childhood idol. I always get asked if I ever wanted to be an astronomer or an astronaut when I show this photo, and the answer is a hard no, because I'm deathly afraid of heights. That's sort of a job requirement to be an astronaut. So I'm the next best thing. I'm an exoplanet astronomer. So let's unpack what that means. So exoplanet, that's short for extrasolar planet. A lot of us astronomers, there's lots of words that are very long, and I'm too lazy to say all those letters. So what we do is we break that up and we slam it together. It's called exoplanet. So extrasolar means beyond the solar system. So anything outside of our own solar system. And planet, you know what that means, hopefully. If not, maybe I'm talking to the wrong astronomy club. So an exoplanet is any planet outside of our own solar system. And then astronomer, you guys all hopefully know what that is. That is someone who stares at the computer or the sky for way too long. And I definitely do both those things way too much. So at JPL, what I do is I'm an exoplanet astronomer. I help develop missions that will be looking for exoplanets, planets outside of our own solar system, to characterize them, to figure out what's in their atmosphere, what their molecules are, what their temperature is, to eventually answer the ultimate question, are we alone in the universe? Because I'm a giant Star Wars fan. I was hard not to go to Disneyland on my way here to Star Wars Land because I love it so much. So I want to ride the Millennium Falcon one day. To do that though, you have to find the aliens and where they're flying. Also guys, I'm wearing a NASA shirt, so giant nerd. If I talk too quickly or if I say something you don't understand, feel free to raise your hand, interrupt me, and I'll try to explain it a little bit better and slow down. So, are we alone in the universe? As we know today, there's only life on one planet, and that's here on the Earth. But the question is there life out there elsewhere? And this question has been answered and studied a lot in the last 20 to 30 years in exoplanet science. Exoplanets is one of the newest fields in astronomy. But despite this field being relatively brand new, it's still been postulated for a long period of time, for hundreds if not thousands of years. For example, in the 16th century, Giordano Bruno, he's that creepy looking dude at the top right there, he postulated a few hundred years ago that there's likely planets outside of our own solar system that potentially could have life on their surface. And Isaac Newton, you know, the guy that discovered fig Newtons, right? In his book Principia, where he discussed the theory of gravity, he said, and if the fixed stars are the centers of similar systems, they will be constructed to a similar design. In other words, we have eight planets in our solar system, because Pluto is not a planet. No booze, you guys are wrong. Pluto's not a planet. Ask me about that later. It's not a planet. So we have 8 planets in our own solar system. So when we walk out into the night sky, we look up all those stars in the sky, it stands to reason that those stars do have planets orbiting around them. And we know that these 2 dead guys are absolutely correct. We now have discovered over 4,000 exoplanets since we started looking in the mid-90s. And as our technology gets better, as we know where to look, how to look, what to look for, we can discover more and more exoplanets with increasing time. So now we know that exoplanets are everywhere. And thanks to missions like NASA's Kepler, which I'll talk a little bit later, that mission has let us know that for every star in the sky, there's at least one planet for it. So there's at least as many planets as there are stars in the sky. And potentially, where there's planets, there might be life. So how do we find life? Well, here's an easy 3-step method that you all can use when you get back home. Step 1, find an exoplanet. Step 2, you have to determine if it can support life. Just because a planet is there doesn't mean that planet has life on its surface. For example, Mars, probably no life. That'd be cool. Venus, probably no life. Mercury, probably no life. Then you have to find an exoplanet and actually determine if it has the conditions necessary to support life on its surface. Then, if a planet could have life on it, you have to make the next crucial step. And this is the hardest step of the three. You actually have to find conclusive detections of life on the surface. And there's a lot of false positives that I'll talk about later tonight that could confuse you and you might think are actually due to life, but actually occur naturally. So let's start off. How do we find exoplanets? There's actually a bunch of different methods that we use to find exoplanets. And the top three that I'll be talking about are these that I'll be talking about tonight. The radial velocity method, the transit method, and the direct imaging method. Because arguably, with these two up here at the top, we know the most about exoplanets to date. And then this method, direct imaging, which I'll be talking a little bit about later, is a big push that NASA is doing with future technologies to find habitable Earth-sized planets. So let's start off with the radial velocity method. So as you might know, light can behave like a particle, and it can also behave like a wave. So light can behave like other waves, like sound waves. So if you're ever walking down the street and you hear like a race car go by or someone driving way too fast down the road, you know how their car pitches up in frequency? That's because the sound waves are compressed as the car comes towards you and the frequency gets higher. Then as the car drives away, the waves are actually stretched out and the frequency decreases. So that's why the pitch goes high when the car comes towards you and then decreases as the car goes away from you. Light behaves the exact same way. So let's pretend we're looking at an extrasolar solar system. So we have a large planet orbiting around this star. And what the planet does is it actually tugs the star back and forth. As the star comes towards us, the light is blue shifted as the light waves are compressed. And as the light of the star comes away from us, it's red shifted. So as we watch the star wobble back and forth, we can then infer that there is an exoplanet tugging on that host star. So just by observing the motions of the star, we can then infer the presence of an exoplanet orbiting around that host star. And this method is really important because this gives us the mass of the planets. So using this method, we can directly measure exoplanetary masses just by looking at the star's light. Importantly, this only gives us motion along the line of sight. So I have to see a star coming towards me or farther away from me. If the star is wobbling in this plane perpendicular to us, we don't see the light changing in its wavelength or its frequency. So this is sort of biased in that sense. So we have to be seeing it coming towards us or away from us. So the advantages of the radial velocity method is it gives us the mass of the planet. The disadvantages, though, is that we're biased towards large planets. Because the bigger the planets, the more they'll tug on their host stars and cause that host star to wobble back and forth. Smaller the planet, the smaller the wobble of that host star. And then also, if you want to look at things that are very, very small, like an Earth-sized planet, we need a large telescope to observe them. So we need things on the orders of 10 meters. These are actually the Keck telescopes on Mauna Kea on the big island of Hawaii. And you need a 10-meter telescope to get to the very precise precision that you need to be able to see an Earth-sized planet orbiting a solar-sized star. So that's the radial velocity method. What's the next method? And that is the transit method. So this is a method that's actually very near and dear to my heart because this is what my whole background is in, is transiting exoplanet science. So for observing a star, if we're lucky, a planet will eventually, wait for it, pass in front of the star and block out the star's light. And what it effectively does is it casts a shadow all the way back on the Earth. And as that shadow crosses in front of the Earth, the star appears to get dimmer. So that decrease in brightness of the star tells us that there's a planet there. But also that dip in brightness also tells us the radius of the exoplanet. The bigger the planet, the bigger the dip. The smaller the planet, the smaller the dip. So the size of the dip, or the amount that the star dims, tells us the size of the exoplanet orbiting around us. So this method allows us to measure the radius of these exoplanets. And then, as I'll talk a little bit later, this also allows us to study an exoplanet's atmosphere, to allow us to characterize how the planet's atmosphere absorbs the light of its host star. And this method has actually produced the most numbers of exoplanets we know today. This method has discovered 3,000 of the 4,000 exoplanets we know of today, mostly due to missions like NASA's Kepler mission, a dedicated exoplanet finding mission, and also many ground-based surveys that have been looking for exoplanets. So the advantages of the transit method is it's actually relatively cheap. You can use a really small telescope to observe a transit. You can use a 3-inch telescope, a 6-inch telescope. I saw someone online that used just a digital camera, and just a digital camera, they were able to observe a planet passing in front of its host star. The advantages, again, is this determines the planet's size. However, exactly like the radial velocity method, you're biased towards big planets. Big planets, bigger signals are easier to see. You can result in false detections, such as stellar activity sometimes might look like a transit. Two stars orbiting around each other can sometimes look like a transit. And then also, you need that perfect geometry. You need to have that edge-on geometry to see the planet passing in front of the star, or else the planet won't cast a shadow on the Earth. So I've been talking a lot about the Kepler mission. This is the Kepler mission right here. This is a dedicated exoplanet finding mission. And what this did is this stared at this little field of view right here for about a year or two. And that size of the field of view is roughly the size of the full moon. So in that little patch of sky, Kepler discovered thousands of exoplanets. So if we extrapolate that tiny patch of sky to the entire sky, that's how we can infer that exoplanets are everywhere. They're very numerous, they're ubiquitous. And there's at least as many planets as there are stars in the sky, thanks to the Kepler mission, which is pretty incredible. Unfortunately, Kepler has died in the last year or so. Its reaction wheels, which help it keep pointed in the sky, have failed with age. But don't worry, because there's another NASA mission that I'll be talking about in a second that's effectively replaced it. So Kepler has discovered the most exoplanets to date. These two big bumps right here are actually two big Kepler data releases of exoplanets, where in 2 papers they released hundreds of new exoplanet targets to our catalogs. So this is the successor to Kepler. This is NASA's TESS mission. This is another mission dedicated to discovering new transiting exoplanets. Whereas Kepler primarily looked at one small portion of the sky, TESS is doing a full sky survey. So TESS will look over the entire sky for new exoplanets. And it's predicted that TESS could potentially discover over 10,000 new transiting exoplanets. So today we know of 4,000. TESS will now more than triple that number of exoplanets, which is pretty incredible. So TESS started observing in the southern hemisphere, and just a few months ago, now TESS is operating in the northern hemisphere, and it will continue to find hundreds, if not thousands, if not tens of thousands of transiting exoplanets. And this mission is extremely helpful because we'll be able to observe transiting exoplanets with the next generation of NASA missions. So Hubble, you can actually use today. It's in orbit since the late 80s, early 90s. It's been observing exoplanets the last 10, 15 years or so. And Hubble is observing transiting exoplanets right now. The transit method will also be used by James Webb. James Webb Space Telescope is the successor to Hubble. This is a truly immense telescope that's about 6 meters from the primary mirror. The bottom, that sun shield, is about the size of a tennis court. It's ginormous, to use a technical term. This is actually just south of LAX right now. They're doing the final checkout of it just south of LAX at, I think, Northrop Grumman. And hopefully that'll be launching in the next year or two. And when James Webb launches, it'll have unprecedented precision of exoplanets and their atmospheres and their measurements of their atmospheres. After James Webb launches, we'll have another mission that'll be launching in 2028. This is a European Space Agency mission called Ariel. And Ariel is a dedicated exoplanet mission that will now look at thousands of transiting exoplanets and their atmospheres. So with Hubble, we've observed tens in detail. James Webb will look at tens to hundreds of exoplanets. Ariel will observe thousands of planets. And the missions that come after that, who knows? Maybe a bajillion, if that's a real number. Or maybe what they'll look at is Earth-sized planets that might have alien life on their surface. However, if you wanted to observe a transit, we have to know when that planet passes in front of its star. So if we think a transit actually occurs here in red, and we plan our observations around that red observation, but we're wrong. Let's say the previous measurement was not that sophisticated, that previous measurement was not that accurate, and it had large uncertainties. What happens if the transit actually occurs here, or even earlier? That runs the risk of us missing the transit completely, or even partially. And last time I checked, wasting NASA time, mission time, is not a good idea. It does not earn you many friends. So this is actually the power of small telescopes. Small telescopes can actually help us observe transiting exoplanets, refine their transit times, and actually allow us to use large NASA missions a lot more efficiently and effectively. So right here, this is actually a sample observation of a transiting exoplanet. So here's the host star. Here's where the planet passes in front of the star, causing the star to dim. The size of that dip tells us the relative area of the planet to the star. So the area of the planet is roughly 2% of its star. So the planet's radius is roughly about a tenth of the star's radius. And then from this data, we can also measure the mid-transit time and then predict with more efficiency when that planet will transit its host star again. Again, this is a six-inch telescope down in Tucson, Arizona. This is a relatively dim star. This is about 11th magnitude. Despite this being a dim star, despite this only being a 2% transit signal, despite this being a 6-inch telescope, we can get really beautiful data. And this is the power of small telescopes. So this is why I'm actually starting a new citizen science project called Exoplanet Watch. So this is a citizen science mission to observe high priority transiting exoplanets. So by people such as yourselves who own smaller telescopes, 3 inches, 6 inches, anything around there, or even larger, using your CCD camera, you can observe transiting exoplanets. You can then measure the mid-transit times. You could feed that into our pipeline and then make that data immediately public to NASA astronomers who are then proposing for NASA mission time. To use that time more effectively, to use it more efficiently, to also enable the achievement of more science by those missions as well. And then if you do an observation for this effort, you will be listed as a co-author on any published paper. I mean, you do the work, you deserve the effort, you deserve the accolades, right? And it'll enable a bunch of science cases, and we're actually starting our testing right now. One cool facet of Exoplanet Watch is we have this data reduction code that was made by one of my interns the last 2 summers called Exotic. This is actually a data reduction code that takes your raw image files and produces a light curve just like this. So this is actually a light curve produced by Exotic. And this data reduction program was specifically tailored for amateur astronomers to make the data reduction method as easy as possible, but also including you in the data reduction process so it's not just like a black box. Another cool feature is that I can reduce data in real time. So let's pretend at your next star party, you want to observe a transiting exoplanet. Well, staring at a star for 5 hours is pretty boring, right? It's kind of hard to see that 2% transit drop. What you can do is you can give Exotic in real time your data, and it will actually produce a transit light curve in real time. So you can point to someone and say, look, we're observing a planet transiting its host star hundreds of light years away right now, which is pretty incredible. So this is actually completely free. It's available right now on the internet. Feel free to come up and talk to me afterwards. And if you're interested in joining and trying out the software, we'd love to have you as one of our testers. But what we'll be doing is that we'll be launching in the spring or summer of this year. I'm hiring a bunch of interns to help out with that. And we need you guys, if you have a telescope, if you have a digital camera that's hooked up to your telescope, to start observing transits for us tonight, even, right after this talk. So no one should be here asking me questions. You should all be observing if you have a telescope, right? And you can use things like Exotic to reduce your data. You upload your data to the Amateur Astronomer Variable Star Catalog Association Exoplanet database. And then if you don't have any data, let's say you don't have a telescope, you don't have a CCD, that's fine. Exotic actually comes with sample data. So you could download the data, install it on your computer, and get a reduced transit light curve that's science grade and publishable, because I'm actually going to be publishing it, that you can look at within an hour. So yeah, come up and speak to me after my talk if you're interested in joining. Okay, I'll get off my soapbox and get back on with the talk. So that's the radial velocity method and the transit method. The third method I'll be talking about tonight is the direct imaging method. So direct imaging sounds exactly like it is. That equals taking photographs of exoplanets. However, there's a big problem. Last time I checked, stars are really, really bright. And they're a lot brighter than their host exoplanets. So the question is, how do you block out the really bright light from your host star so you can see the light of the exoplanet itself? So let's do a little thought experiment. Let's take a sun-like star, and let's take a big planet that's really hot. And therefore, since it's really hot, it's really bright, it's really big, so it's easier to see. Now, if we put that hot extrasolar planet, that exo-Jupiter, around that sun-like star, it's actually really hard to see. Its light is 1,000,000 times fainter than its host star. That's like looking for the light of a firefly flying around a lighthouse. That's pretty tough. Okay, now let's replace that Jupiter with now an Earth-like exoplanet. Put it around our same star. Well, that exoplanet, that exo-Earth, is 10 billion times fainter than its host star. That's like looking for one alga around that same lighthouse. So the question is, how do you get rid of that annoying star so you can see the cool stuff like exoplanets orbiting around them? And this is exactly what I do. I am on a mission called W-FIRST CGI that uses technology, new technology that actually is able to block out the light from the host star so you can see the light of the exoplanets orbiting around them. How many of you guys went to the solar eclipse a few years ago, or at least saw it? Nice. So remember how during the solar eclipse when the moon passed in front of the sun, you could see some of the stars around the sun, or you could see the solar corona? We can do the exact same with exoplanets. So here's an exoplanet host star. If you block out its light, you can now resolve the light of the exoplanet orbiting around it. So we sort of make a simulated eclipse where we block out the light of a star with basically a moon or a coronagraph. And as that blocks out the light from the star, it allows us to resolve, to see, to uncover the light of the planet orbiting around that star. So there's a cool video that I'll sort of narrate along here. This is for a mission called W-FIRST that I'll be returning to in a little bit. So a coronagraph works by blocking out the light from the host star. So if we now take the light from that star and shine it into our instrument, we need to sort of feign an eclipse. We need to basically block out the light of that host star. So we can do that by adding a thing called a pupil. And the pupil blocks out the light of the star. And then we effectively add another piece, a washer. And the washer basically blocks out the residual light of that star. And that does a really great job of eliminating most of the star's light. But there's still some imperfections in the telescope. So what we do is we use a deformable mirror. This is a very, very thin sheet of glass that has a bunch of pistons behind it that wobble at their frequency to make that bending light straight. So you can see all those imperfections. When we activate our deformable mirrors, you can see the image quality starts to improve. And that takes out the residual scattered light inside our telescope. And then, with many, many observations, you can then start to see the light of your exoplanet orbiting around the star. So by blocking out the central light of the star, by blocking out residual light with that little washer basically, And then using deformable mirrors, we can then look at exoplanets, much dimmer, millions of times dimmer than their host star, and then observe their light. And this is actual direct imaging data. So this is data from an instrument at the Gemini Observatory. It's an 8-meter telescope. So right here's the central star. They've blocked out the light from the star, and each of these 4 little dots are actually exoplanets orbiting around its star. If you look down here, this is data taken over 7 years. So you're seeing in real time these planets orbiting around its host star. You guys should be going ooh and ah right now. There we go, thank you guys. Making sure you're still awake here. So I'm actually pretty jealous of direct imaging because of transits, I never see my exoplanet. But direct imaging, there they are. Look, there's the exoplanets. It's pretty cool. So we can use the direct imaging method to directly null out the star's light to observe the light emitted or reflected by their host star. Okay, so now what? I've talked about 3 different methods that we can use to find exoplanets. And using these methods and others, we've discovered over 4,000 exoplanets to date. But now we want to make the next step from planet detection to now planet characterization. We want to answer questions like, how doesn't a planet have an atmosphere? If so, what molecules are present in that exoplanet's atmosphere? Could that atmosphere support life? And if so, does that exoplanet have life on its surface? So to answer these questions, we actually use a physical law that allows us to study the atmospheres of exoplanets. And that's called Beer's law. And that law allows us to determine if a planet can support life. So we can use these 3 methods to find exoplanets. We can use those other methods as well. And now we want to take the next step to determine if a planet can support life by looking for molecules in that planet's atmosphere to see if that planet has methane, CO2, carbon monoxide, water, to see if it has the elements, the molecules that are necessary to support life in its atmosphere. So how do we figure out what molecules are in an exoplanet's atmosphere? We could take as a first step by figuring out where planets are in their solar system. So you might have heard a lot about the habitable zone. This is also called the Goldilocks zone. So this is the zone where liquid water can survive on a planet's surface. So right here, this is a down-looking view of our own solar system. There's the sun. Mercury and Venus are a little bit too close to the sun. They're way too hot. Liquid water can't survive on their surface. Mars is a little bit too far away, but Earth is in the just right orbit where we can have liquid water surviving on its surface. And the reason we care about the habitable zone, the reason we care about the Goldilocks zone, is because life as we know it requires liquid water to survive. This is definitely applying an Earth-centric view on other exoplanets. But as far as we know, life only exists on the Earth. And as life as we know it on the Earth requires water to survive. So that's why we're looking for planets in the habitable zone. And this is why we were very excited about the discovery of this exoplanet system called TRAPPIST-1. This is a multi-planet system. And these 3 planets right here that are all Earth-sized planets are inside the habitable zone of their host star. So perhaps these 3 planets, one of them or all of them, might have life on their surface today, which is pretty incredible. We might have already discovered the exoplanet system that has life on its surface. So that's all well and good. That's sort of narrowing the net of saying, okay, what planets are likely to host life on their surface? The ones that have liquid water on their surface. But how we take the next step by saying they're in the right location, to saying definitively what's in their atmosphere, if they have water, if they have methane, if they have CO2. And we actually use a physical law for that called Beer's law. So this is a little technical, so bear with me for a second. So here's the definition of Beer's law. Studying for a test or doing homework while beer is involved, making difficult classes just physical chemistry more bearable. That's a good Beer's law. I did that a lot in grad school. That's not the right Beer's law. Here's the right Beer's law. What it does is it essentially describes the scattering of light in and out of a beam. So let's pretend we have a light bulb right here. and a tube of gas in front of the light bulb, maybe filled with something like methane. Now, when we observe the light from that light bulb passing through the tube of gas, we would expect the light to be absorbed or scattered by that tube of gas. And it actually follows that law right here. And depending on how that light is absorbed or scattered as a function of wavelength, we can actually back out the material that is causing the absorption or the scattering. So another way to think of it is, let's pretend we're an astronomer and we're observing a yellow star. What color would you expect that star to look like through your telescope?
Yellow.
Yellow, very good. Okay, good. You're all laughing, but here comes the next harder question. So now let's replace, between us and the star, let's now put a giant cloud of gas or something. Would you expect the light to be as bright or dimmer? Would you expect the light to be yellow or a different color? Same or different? Very good. You guys are passing so far 100%. Right. So the cloud of gas will absorb or scatter some of the light from the star and cause it to look a little bit dimmer, maybe a little bit redder. So if we observe what an object does look like and compare it to what the object should look like, we can then use Beer's law to actually figure out what the composition of the absorber is. So you can actually infer and figure out that this gas cloud, for example, has molecules in it. So let's now take an exoplanet. Let's take a really young exoplanet. When exoplanets form, they sort of condense from all the gas and dust in their nebula. And all of that gas and dust starts to condense. They all rub up against each other and cause friction, which then gives off heat. So young exoplanets actually have very hot cores. And these hot cores radiate out heat and light. And as they radiate from the center to the exterior of the planet, they pass through outer layers of the exoplanet's atmosphere that are a little bit cooler. And therefore, the light that was once yellow starts to turn orange, getting a little bit more dim, until it finally emerges from the exoplanet as red light. And then astronomers at the other end of that telescope can say, holy, that planet has methane in its atmosphere. Alternatively, we can look at a planet reflecting light from its host star. So this light is shining yellow light at this Jupiter-like planet. And because of clouds, because of methane in Jupiter's atmosphere, it'll reflect light at certain wavelengths alone. And then we can look at that reflected light, compare it to the light that was emitted by the star, and then we can use Beer's law to then say that that planet has clouds in its atmosphere. So just by purely looking at light, by observing how an exoplanet's atmosphere absorbs, reflects, or scatters light, emits light, we can then infer, we can calculate the composition of an exoplanet. So that's how we can figure out what an exoplanet is made up of without even having to go there, which is really handy because they're millions of miles away, and I don't have enough freaking flyer miles for that. So here's actual exoplanet spectral data. This is measuring the light of a few exoplanets, about 9 exoplanets. On this axis, we have a bunch of different exoplanets. On this axis, we have basically their brightness. So hot planets are at the top, cooler planets are at the bottom. On this wavelength, they've plotted here a function of wavelength. So this is analyzing the emitted light of these exoplanets over various wavelengths of light. And this is really important. Spectroscopy is important because it allows us to study how an exoplanet's light varies with wavelength. And this is very important because at these wavelengths right here that I'm showing in blue, these are associated with water absorption. So water absorbs very strongly at these 3 wavelengths. So if I see a bump and wiggle at these wavelengths, I can infer that that planet has water in its atmosphere. These wavelengths correspond with methane, and then this wavelength here corresponds with carbon monoxide. So just by looking at how the planet absorbs, emits, or reflects light, we can then use Beer's law to figure out what molecules are doing that absorption. And that's called exoplanet spectroscopy. So some of you eagle-eyed observers might have noticed we have these little gaps in the data. Can anyone guess what these gaps are? rhymes with the Earth's atmosphere? Anyone? Rhymes with Earth's atmosphere. Rhymes with Earth's atmosphere. I'm giving you the biggest hint, guys. You still aren't saying it. Earth's atmosphere, good job. This is exactly where the Earth's atmosphere absorbs light. So the Earth has really annoying things like water, carbon dioxide, oxygen, methane, all that annoying stuff. It gets in the way. And it absorbs a lot of light in the infrared at these wavelengths. So, just like looking through a fence, we can only look through the gaps in the fence, the gaps in the Earth's atmosphere, to observe the atmospheres of exoplanets. Otherwise, the Earth's atmosphere absorbs light too strongly at these wavelengths, and they're effectively invisible to us. So if we can't observe it from the ground, what's the logical next step? Exactly, go into space. So this is exactly what's been used by the Hubble Space Telescope. This is why Hubble is so important, because it allows us to observe above the Earth's atmosphere, outside of the absorption of the Earth's atmosphere. You might have heard a lot of stories, for example, about the discovery of water on exoplanets. And the reason for that, there's just an instrument called the Wide Field Camera 3, and that has the wavelengths that correspond with water absorption. So the reason we're finding or not finding water on all these exoplanets is completely because we're biased by our own instrumentation. Because Hubble has an instrument that is designed to look at those wavelengths. But most of these exoplanets do have water in their atmospheres, which is pretty cool to think about. So here's actually 30 exoplanets. These planets have water, and some of them have very flat spectra. So there's a bump here and this bump here indicate that there's water, the little twin bump feature. This exoplanet has a very flat spectrum. And what that is actually high altitude clouds that block out the light from the water, the absorption by the water. So these planets are very clear skies. These are very cloudy skies. So in just 20 to 30 years, we've gone from exoplanet discovery to now looking at weather on exoplanets. So all of these planets likely have water in their atmospheres. These are just too cloudy for us to see below the clouds to see the water absorption. But these planets are all too hot for liquid water to exist on their surface. These are all water gas in their atmospheres. So that's called transit spectroscopy, looking for those bumps and wiggles that correspond with the molecular absorption features. Another mission that some weird guy named Zellem et al. In 2014 published was this paper of the Spitzer Space Telescope. Spitzer was just decommissioned about 2 weeks ago. It was a JPL mission, and it allowed us to study exoplanets and stare at exoplanets for hundreds of hours. So this is about 100 continuous hours we've observed this exoplanet system. So here's where the planet passes in front of the star. Here's where the planet actually passes behind. These planets are so hot and so bright they radiate their own light, and actually an amount that we can actually observe. And this panel is the top panel, just zoomed in on this region right here. So this bump here indicates that this side of the exoplanet is a lot warmer than this side of the exoplanet. And we can measure the difference between this bright day side and this dim night side, and we can determine that the temperature contrast between these two sides of these exoplanets is on the order of 400 degrees. So what that does is it sets up a huge temperature contrast, and all that hot air rushes to the cold side as it tries to equilibrate the temperature of the planet. And actually those wind speeds break the speed of sound on this exoplanet. So intense weather on this transiting exoplanet. And both of these methods, the transit method, looking at phase curves such as we just looked at with Spitzer, they'll be used by the James Webb Space Telescope to observe up to 100, if not 200, transiting exoplanets. And we're all very excited about the launch of James Webb because it'll have unprecedented precision that we've only dreamt about so far with Hubble and Spitzer. Then looking beyond James Webb, which will be launching likely in 2021, we have the WFIRST telescope. This is a Hubble-sized telescope that'll be launching in 2025. And this mission will be looking at astrophysics, dark energy, and excitingly for me, exoplanets. So I work on a specific instrument on WFIRST called CGI, the chronographic instrument, on the project science team. So what CGI will do is it'll allow us to demonstrate that direct imaging technology that's worked and been demonstrated so far only on the ground also works in space. So currently with ground-based telescopes, we're limited to looking at hot, bright, large planets really far away from their star. That's because it's easier to block out the star's light without getting in the way of the light of the planet. What WFIRST will do is it'll allow us to look at cooler targets closer to their host star. So they'll be able to push us towards closer to the inner solar system of these exoplanets. These are cooler objects, roughly the same size, but a lot closer to their star. And CGI is an absolutely necessary stepping stone to achieve the ultimate goal of looking at Earth-sized planets orbiting around their stars. So CGI provides that stepping stone from where we currently are today to where we want to be in the next few years of future NASA missions. And this will allow us to then definitively look for Earth-sized planets that might be habitable and answer the question if we are alone in the universe. Another mission I'm looking forward to is ESA's Ariel. This is the European Space Agency's mission. This is a mission that'll be looking at 1,000 exoplanets. And we actually have a contribution that was just accepted by NASA a few months ago that will provide some additional capability Ariel. And what Ariel will do is look at 1,000 exoplanets. So currently Hubble's looked about 40 to 50. James Webb will look at 1 to 200 in unprecedented precision. Ariel will look at about 1,000. And it'll look at those 1,000 and put those James Webb observations into a much larger statistical context. So why do we even bother with the ground? You can do all this cool stuff up in space, right? Right? Why do we even bother going to places like Palomar or Hawaii or whatever? You know, because you don't have to worry about the Earth's atmosphere. You don't have to worry about that stupid thing called the sun. But there's only a few space-based telescopes. You know, there's Hubble, there was Spitzer, we're still waiting on James Webb, there will be WFIRST. There's a very limited amount of telescopes, and there's a lot of scientists that are trying to get on these telescopes, deservedly so, to do very interesting science. So we're all fighting for time on these very limited resources, and that's where ground-based telescopes can come in. Ground-based telescopes, there's so many more of them. That's a lot easier to get time and to sort of spread the wealth of all the science over all these telescopes. However, you do have to worry about the Earth's atmosphere, and there can be large uncertainties as you look through the Earth's atmosphere when you're observing these exoplanets. So that's why I still love doing ground-based observing, because I'm very fortunate that I actually get to use the 5-meter, the 200-inch telescope at Palomar Observatory. And what I'm doing right now is I'm commissioning an instrument called NESSI that's actually at Palomar right now. And I'll actually be out there in a week and a half to observe a transiting exoplanet or 3. So we have an instrument called NESSI, the New Mexico Exoplanet Spectroscopic Survey Instrument, or NESSI for short. It'll be looking about tens of exoplanets. So right here, here's a picture of the NESSI instrument. No, that is a imaginary sea creature. Let's find a real picture of NESSI. That is the actual instrument NESSI. If you've ever been to Palomar, this is in the electronics lab at Palomar Observatory. There's the instrument on its handling cart. I'm actually doing some testing by taking some photographs of the ground. There's its computers. There's the liquid nitrogen. This instrument operates at the infrared. In order to keep the heat down, we pop it full of liquid nitrogen. And that's because heat gives off infrared heat, infrared light. So to avoid the instrument from interfering with itself, we have to cool it down to way below freezing with liquid nitrogen up there. So here's actually a picture of NESSI as it's being lifted up into the prime focus cage at Palomar. So normally on a telescope, when you think of it, light comes in, hits the large primary mirror, gets reflected, hits the secondary mirror, and then there's an observer or an instrument at the very bottom of the telescope. NESSI is unique comparatively in that it sits at the top of the telescope. It replaces that secondary mirror because it preserves a large field of view for our instrument. So that means we get to lift NESSI from the ground all the way above the Palomar 200-inch telescope. So right here is the instrument PI, the principal investigator. That's Michelle Creech-Ekman. She's a professor at New Mexico Tech. She has a really cool shirt on. I want to believe it's a picture of Nessie. I like that shirt. There's my boss not paying attention to me like normal, taking a cool photo of Nessie instead. It was a cool photo. So as Nessie is now lifted up through the air, we're all hoping that our insurance policy has started at this point, because that is a very large, historic telescope mirror that our instrument is being lifted over. Luckily it made it, okay? I'm not bankrupt. How do we do that? With a giant crane that's just out of the shot of the photo, which is actually a big crane that is specifically designed to lift instrumentation up to the prime focus gauge, which is right here. So the light comes in, hits the primary mirror, reflected up, and normally with a secondary mirror would be NESSI is now installed here in the prime focus gauge. So light is directly reflected from the primary mirror up to NESSI. So there's my boss, Mark. There's NESSI in the prime focus gauge. This is our first ever fit check. We're very happy that it actually fit where it was supposed to. Mark is smiling, but he's mostly laughing. Because remember, I'm afraid of heights, guys. But I'm the commissioning lead for NESSI. So guess who gets to go up to the top with a telescope every time on this rickety bridge thing that was built in 1948, and which occasionally breaks when I'm on it? I do. So he's really laughing at me because I should probably wear a second pair of pants. Let's just leave it at that. But I got a really cool photo of NESSI. There it is in the prime focus gauge, and there's my feet in it too. It kind of looks like a spacecraft, so I thought it was really cool. And we finally, just a few months ago, got our first ever transiting exoplanet data with NESSI. So right here is the host star. That's what the planet blocks with the star's light. And this is roughly getting into a factor of 2 of the precision of Hubble. So the ground-based telescope, the giant telescope, we're actually getting pretty close to Hubble's precision, which is pretty incredible. Okay, so that's how we find an exoplanet: direct imaging, radial velocity, or transits. We can use Beer's law to determine if that planet has molecules in its atmosphere, the building blocks that could potentially support life. But how do we go from the next step and now actually definitively find life on that planet's surface? Well, we can do a few things. For example, we can launch a mission out into space, and as it's traveling out into the solar system, we can have it turn around and point itself back at the Earth. We can have it look at the Earth's spectrum. We can see how the Earth absorbs, emits, and reflects light as a function of wavelength. We can use Beer's law, and we can actually figure out, do we see evidence of oxygen being produced by algae? We could look for liquid water on its reflectance spectra from the Earth's oceans. Or maybe we can even look for other things like cow farts, right? You could look for methane. You can look for signs of biological activity. However, you have to rule out all other explanations. We're finding methane currently on exoplanets. We're finding water on exoplanet atmospheres. But all these planets are too hot for life as we know it to exist on their surface. So that is the real catch-all, is you have to rule out all other explanations to definitively say if that planet has life on its surface. Or we can do then a really cool / sexy thing. We can directly talk to aliens. That's pretty cool, right? So Voyager 1 and 2, they were launched in 1977. And they had that grand tour of the solar system. Just a few days ago was a big anniversary of the pale blue dot image taken by Voyager. That was pretty cool. And they had these golden records on board right here on the side of Voyager. This is a JPL mission, so I'm going to talk about it. And this golden record is really cool because it tells the aliens how to play it. There's your little phonograph right here. This gives you the frequency that you need to play it. This is how you display images on your alien TV set. There's hydrogen, because why not? And then right here is the location of the Earth respected to a bunch of different pulsars in the solar system, or in the galaxy. So this record on it actually has various recordings of humans saying hello and other greetings, and also photographs of Earth life. So basically what this says to aliens is, hey guys, here we are, this is what we look like, come on, invade us, because here's where we live. So those are sitting right now on Voyager 1 and 2. Another way we can do is we can actively send messages to aliens. So back in the mid-70s, Frank Drake and Carl Sagan actually wrote a message to aliens using the Arecibo Observatory. At the time, this is the world's largest radio telescope. This actually sits in a valley between mountains on Puerto Rico. And they sent this message to a globular cluster. This is hundreds of thousands of stars orbiting around each other. And they thought, hey, there's lots of stars, there's likely a lot of planets. Unfortunately, now we know today, actually that's not the case. These stars are orbiting so close to each other that any planets that form inside are gravitationally ejected by the other stars. So actually planet formation inside a globular cluster is very rare. It wasn't until just a few years ago that we discovered the first exoplanet inside a globular cluster. But that might have been for the best. I'll come back to that in a second. So right here is the message we sent to aliens. Right up here, this is saying, hey aliens, we know how to count. You know about molecules and elements? Can anyone guess what the red thing is? Person? Yep, very good. Can anyone guess what the purple thing is? Yep, that's Arecibo. Purple thing is Arecibo. What about this yellow thingy here? Rhymes with solar system, anyone? Solar system, good job. This is our solar system: Sun, Mercury, Venus, Earth, elevated, because that's where we're from. Mars, Jupiter, Jupiter, Saturn, Uranus, Neptune, and this is back in the 70s when they didn't know any better. They still thought Pluto was a planet. But we know today Pluto's not a planet, so this is all wrong, right? That shouldn't be there. Anyone guess that this blue and white thing is up above the person? Hint is it's a double helix. DNA, very nice. So what this message is saying to aliens is, hey aliens, here's where we are. Here's what we look like. We know how to count. We know about molecules and stuff. We know we came from DNA. Here's where we live on the Earth. Here's how we send our messages. Come and invade us and destroy us, right? So there you go. Maybe it's a good thing that there's no planets out there that could enslave us one day. Another thing you can do is send messages to more exoplanets we've discovered recently. So back in 2008, they sent 500 messages or so to this extrasolar system called Gliese 581. And they chose this system because exoplanets C and D are in the habitable zone of their host star. So C and D might have water on their surface. C and D might have life on its surface. So why not send messages from social media out to those aliens? Because nothing ever bad happens on the internet, right guys? So they send those 500 messages to aliens. Selfies, yep, sure. Oh my God, I hope not. And this system is 20 light years away. So the messages will arrive in 2029, and if the aliens immediately reply with maybe more selfies, we'll get it back to Earth in 2049, which is kind of cool to think about, and mostly scary to think about, that our first contact with aliens will be hashtags from the internet. So the question is, where are we now? Okay, where are the aliens? So unfortunately, despite what the History Channel will tell you, we have yet to conclusively make any detections of extraterrestrial life. Okay? We only know about life on one planet, and that is here, the Earth. And the question is, why haven't we found life? There's so many planets out there. Planets are ubiquitous. Why haven't we found aliens out there? Well, maybe our technology isn't good enough. It wasn't until the last 20 to 30 years that we started discovering the first exoplanets. Despite astronomy being a field of study that's over hundreds of years old, it wasn't until our technology got good enough that allowed us to see the light of these extraterrestrial worlds. Or maybe we just haven't found them yet. Maybe they're talking from over here and we've been looking over here the entire time. Jill Tarter, she's a SETI scientist, and she was the inspiration for the heroine in the book Contact, the movie Contact by Carl Sagan. She gave a really great description of it. If we took the entire universe and shrunk it down into the Earth's oceans, today we've only observed and explored the equivalent of a cup of water. So while we think we know a ton about the universe, there's still a lot more for us to understand and explore. Or maybe most depressingly, to leave you all on a high note, maybe you are all alone. I personally don't agree with this one. I'm very optimistic. I think that would be an immense waste of space if there's only life out there. So I'm a lot more optimistic, and I don't agree with my own bullet point there. So looking at this, we've had this awesome foundation given to us by ground-based observing. This awesome foundation given to us by missions like Hubble, by Spitzer. We found thousands of exoplanets of Kepler. We'll find tens of thousands of exoplanets of TESS. James Webb will look at about 100 to 200 of them in unprecedented precision. Even Earth-sized exoplanets, James Webb will start to characterize the atmospheres of those exoplanets. WFIRST and CGI in particular will allow us to take that next technological stepping stone to being able to look at Earth-sized planets. And right now is a very exciting time in astronomy because there's some new missions that are up for selection. There are 4 flagship missions under consideration by NASA, and 3 of them, these 3 right here, are actually explicitly designed to look for life around other worlds. I've actually been really lucky enough to work on 2 of them, HABEX at JPL and Origin Space Telescope as well. And these 2 missions rely upon direct imaging, and then this mission right here primarily uses the transit method. But all 3 of these missions are explicitly designed to find Earth-sized planets and then to take the next step and to finally answer the question, are we alone in the universe? So thank you so much for your time, and I'll take any questions.
1973 with Carl Sagan and Albert Hibbs of JPL. I was a laser expert, and Carl was very interested in using the lasers to contact other people by sending messages out. Albert Hibbs countered his argument by saying, in Earth's experience, whenever 2 civilizations have met, the more technological superior one wins out. And since presumably the aliens would come to us, they would be better prepared technologically, and therefore Hibbs discouraged advertising ourselves.
Yeah, so basically the comment was that you were very lucky enough to be at a conference with Hibbs and also Carl Sagan. And there are many various ways, some I talked about tonight, that we can actually make known our location, our presence to other extraterrestrial life. And you mentioned one of them being lasers. So yes, you could actually take a super powerful laser and take the equivalent of a large percentage, if not all, of the Earth's power and make our presence known to alien life. There's actually a few scientists working on this today by looking for those signals given out inadvertently or on purpose perhaps by alien civilizations to let their presence be known. But as you mentioned, yes, there's the caveat. If they can send out and have that giant technological leap, they're probably more complex than we are, and we always haven't had the best track record with technology, so there's always that balance there as well. Hopefully they'll be nice to us, hopefully. Okay, next question was over here.
Yeah, it's profound, of course. We think that Earth's been here 4.5 billion years. It's only the last 100 years that we lit up the dark side of the Earth. That NASA image of the Earth at night is really profound, but has there been thought, I'm sure there has been thought, but any thoughts on that, using that in direct imaging to use as potential confirmation that there's some kind of life there of a non-natural transmission?
So if we look for non-natural light, for example, on the dark side of the Earth today, we have all of this lovely light pollution that we have to deal with, especially in the LA area. Can we use these detection methods to actually search for alien life? And the answer is yes, but way in the future. The amount of the light that's given off is, at this point, it's unattainable for us to see and to observe, but potentially if new technology in the future, we can get to the precision necessary to potentially see light given off on the dark side of these exoplanets. So that'd be super cool. Next question, I think, from over here in the middle.
The lay media in the last few days said that there were some regular pulses received here on Earth. What is that?
There were some regular pulses received here on Earth, and they were probably, let's see, they were fast timing radio pulsars, if I remember correctly. Maybe that's what my iPhone said to me one morning. Yes, they are actually happening. Yes. But it's probably something that's very natural, a common occurrence that we're seeing. They occur, I think, on time orders of days, if not weeks. 16 days, so about a week or two. And the current thinking is that if that wouldn't be a frequency used by intelligent life to let us know about their existence, because it's just a very inefficient way of transmitting data, transmitting information. So always the problem with finding extraterrestrial intelligence, with finding aliens, is you have to definitively prove it. And you have to prove it beyond any reasonable doubt. So it's a very hard thing to do. So likely that's natural. A lot of these things that we're discovering today, you could potentially confuse them with being alien in origin, but most of them are likely natural from their occurrence. So a lot of people, for example, are applying a lot of funding into something called biosignatures. These are the molecules, the atoms, the signatures, the spectroscopic signatures that are given off if life exists on an exoplanet. So these are things that are given off regardless if the life is trying to or not. They're sort of byproducts of life. So that way, if you see this bump and wiggle, you can definitively say that life exists on the surface of that exoplanet. And that's an outstanding question of our day is, what are the biosignatures we need to be looking for? What technology do we need to look for these biosignatures? And what instrumentation will have the precision necessary to see these signs of life? Really good question. Thanks.
So are you looking for red dwarfs for any of the exoplanets?
Am I looking?
Carter said that she thought there'd be more of a chance with red dwarfs finding exoplanets.
Am I looking for more exoplanets around red dwarfs? So the TESS mission is actually primarily aimed at looking for exoplanets around small stars. The reason we're looking around for exoplanets around small stars because there's a lot more small stars than there are stars like our own sun. So therefore, if there's more stars, there's likely more planets, potentially there's more life. Also, small stars are easier to find exoplanets orbiting around them because they're smaller, they're dimmer, and also when a planet transits it, an Earth-sized planet will provide a 1% transit depth. Whereas if we took that same Earth-sized planet and put it around the size of our sun, it's 100 times smaller, if not 1,000 times smaller. So it's easier for us to observe Earth-sized planets around small stars. So absolutely, TESS is looking for exoplanets around M dwarfs and planets that we'll be looking at James Webb and definitely beyond. Really good question. In the front.
With all this technology and breakthroughs, do we see anything with creation of solar systems and planets, any advances in that area?
So with all these new technologies we've been using, do we see any new advances in the discovery of the formation of new extrasolar systems? And the answer is totally yes. So there's a lot of great work done, radio, X-ray, visible, infrared light, that actually can observe exoplanetary systems forming in real time. So they actually see a giant cloud of dust and they see an area where an exoplanet has carved out a little ring where there's no dust because all that dust is collapsed on the exoplanet's surface. So with current technology of direct imaging methods, the other large telescopes and other techniques, we're definitely able to now finally actually see planet formation in real time, which is super exciting. I think I saw another question here.
You keep referring to the habitable zone, which I get. You also seem to also refer to Earth size. So is the size important for the possibility of habitability?
So is the size important for habitability, or is it just the location? And the answer is, as far as we think of, it's both for life to be forming on these planets. So admittedly, that is applying a totally Earth-centric idea, a very human-centric idea, to how life forms in the entire universe. But as far as we can tell in our own solar system, life only exists on the Earth. The Earth is, by definition, one Earth size, and it is in the habitable zone of our star. So that's why we're looking for Earth-sized planets in the habitable zones of their host stars. However, life could exist today, for example, on the moons of Jupiter or Saturn. There's some moons, for example, Europa and Enceladus, that actually have large oceans underneath their surface of ice. And potentially there could be life in these ocean worlds. And that would be completely revolutionary because it'll totally change how we think of the conditions that are necessary to forming life in the universe, which will then absolutely change what we look out for when we're looking at new exoplanets. Great question.
One of the first graphics you showed the exoplanet orbiting around the star, and the star was being tugged around by the, actually in opposition of the location of the exoplanet. Is that something, is that accurate? It seems like the planet would be closer rather than farther from us.
So he's asking about this slide, so let me run to it really quick.
It's one of the very first ones.
There's a lot of joke slides to go through, guys, so give me a second. A lot of bad jokes here.
Yes, that's the one.
Yes, there's a lot of bad jokes in this, or?
That's the right slide. There you see that they're on the opposite sides of the circle.
Yeah, so in this image, this is also inflated. The planet and the star are not to scale. The star should be much bigger than the planet, but it's just easier to see in this case. He was asking, when the planet is on this side, the star seems to be on the opposite side. And you would expect that if the planet is truly tugging the star and the planet should be both on the same side of their orbit, right? What actually happens is that the planet and star are orbiting something called the barycenter of their orbit, which is the very center of their orbits. So by physical laws, by solving theories of gravity, actually the star would appear on the opposite side of the exoplanet on its baryorbit.
Is that wobble something that could be used to determine that there's planets around the star?
So yes, we can use the wobble of the star to directly infer that there's planets orbiting on the star. So as we watch the star's spectrum wobble back and forth, we can then infer that something is causing the star to wobble, and then we can then infer the mass of the exoplanet that must be causing the wobble to form. This is also what we can use to find multi-planet systems. A single planet will cause a nice, beautiful sine wave, where if I had a second planet, there's an additional sine wave that's then added in to that signature. So we can actually find multiple planets that way as well. Just by looking at the wobble, as you said, we can look at the wobble of the star's light to then infer the presence of an extrasolar planet. Good question. I think I saw another one in the back. We have another one in the back? Another question? No? Okay, in front.
So just to confirm understanding or maybe misunderstanding, when a transit's observed, it should correlate with a redshift. And is that in fact, both those data sets are available to do that? And how much input is there to confirm we know what we're looking at?
So the question was, if we see a transit, such as here, the planet is passing in front of the star, and that infers that alignment of the planet and the star. When we observe a transit, do we also see a radial velocity effect? And the answer is yes. So a lot of these planets, if we're able to measure their radius, if they're big enough in mass, if we have the right instrumentation that gets to the right precision, we can then, after observing a transit, we can then observe a radial velocity signature of these exoplanets and actually measure their masses. So if we use the radial velocity to measure their mass, use the transit method to measure their radius, we can actually measure and estimate their bulk density. So we can see if they're rocky, if they're icy, if they're gassy. And then we can use Beer's law to actually understand the molecules that are present in that planet's atmosphere. Yeah, so absolutely a great question. So a lot of radial velocity planets were measured first and discovered first, and then we discovered them with the transit method, and vice versa. There's a lot of planets that we discovered first with the transit method, and then use radial velocity measurements to then measure their masses. Really great question. Anyone else? I'll be hanging out up here if you have a question for me too. Oh, yeah, up here in the front.
What inspired you to become interested in planetary science?
What made me a giant nerd that I am today, I think was the question. I'm wearing a NASA shirt, so I thought that would be kind of obvious. So since I was ever a little kid, so I've always been interested in space and astronomy. I've always loved looking at the night sky, like walking my dog as a kid. I look at the stars and think, oh man, there's other aliens looking back at me. I've always loved Star Wars, especially. Absolutely love Star Wars so much. I have a Star Wars hat in the back that I would be wearing right now if I wasn't giving a talk. I love it. And I just never grew out of it. And actually, I was an amateur astronomer first as a kid, and in high school and college. And amateur astronomy really reaffirmed my love of astronomy, and that eventually made me want to study astronomy in undergrad, and then eventually get my PhD in planetary science. So the reason I did planetary science as opposed to astronomy is I met really cool people like Guy Consolmagno, like Levine, other people, planetary scientists in my field, and I thought it was so cool that they could actually build a spacecraft and send it out to the planet that they were studying, where I was stuck in the cold observatory looking at a bright dot in the sky. Then as soon as I got into my PhD program in planetary science, I realized I miss being in that dark, cold observatory looking at the dots in the sky. So I switched, and I had the best of both worlds. I'm now studying planets that I can never see, and I can never go to, but I still get to work on missions. I still get to work on instrumentation. I still get to work on telescopes. So it's really the best of all worlds for me. Any other questions?
How far away are the nearest exoplanets?
How far away is the nearest exoplanet? 3.26 light years away from us, which is hundreds of millions of miles away. So for context, the sun is the closest star to us, right? The sun is 8 light minutes away. So it takes light 8 minutes to go from the sun to the Earth. If the sun were to magically turn off one day, we wouldn't know about it for 8 whole minutes. So if you were to go to Proxima Centauri, for example, that's about 3 light years away. So even if I were to travel at the speed of light, it would still take me over 3 years to get there. So if I look into the universe, I'm seeing that light as I looked at 3 years ago. And the farther I look into the night sky, the farther back in the past I'm looking as well. We're getting one more question.
What is the most astonishing or impressive thing you've learned about the universe?
What is the most impressive or astonishing thing I learned about the universe? So this is probably the one thing that I was pretty amazed at looking at, because, so this is HD 209458b. This is a hot Jupiter, a large Jupiter-sized planet orbiting very close to its host star. So it's very, very hot. Thousands upon degrees Fahrenheit, this planet is orbiting around its star. This planet orbits around its star every 3.5 days. This is 10 to 100 times closer than Mercury is to our own sun. So that means that I can actually observe transits of this exoplanet about once a week. So a great target to look at if you're trying to get out of Tucson in about 5 years. So you only have to wait about a week between your observations. Very handy. But if we take Spitzer, we could actually look at this target continuously over 100 hours. And this was the first ever what's called a phase curve of this exoplanet. This is monitoring the variations in the planet's brightness with its longitude. So this side, as I said before, is very, very hot. This side is actually tightly locked to its host star. So there's one side of the planet always facing its star, just like the moon always faces one side of the Earth. This planet is tightly locked to its star. As a result, one side gets very, very hot for 2,000 degrees Fahrenheit. This side is comparatively cool. It's always facing away from the star. It's radiating all that heat away into space. And like I mentioned before, that sets up a huge temperature contrast between the hot side and the dark side. It's about 400 degrees. What sets up those supersonic winds that transfer all that heat from the day side to the night side. So we're actually able to observe climate, weather physics on extrasolar planets. And this data set done by that weird Zellem et al. Dude is actually the first time we ever observed this exoplanet using this method. So I was kind of proud of that.
So how big is the planet?
The planet is about the size of Jupiter. And the star is about a K-dwarf, so it's about roughly the same size as the sun or so. Yep.
Does it radiate more than it reflects?
So this planet does radiate some heat. As you mentioned, does this planet radiate heat or radiate more than reflects. This planet is primarily getting its heat source from the star since it is so close to its host star. It does likely have some residual heat from when it formed that is still radiating away. So if you turn off the star, it would probably still attempt to glow a little bit. But this exoplanet is primarily, almost overwhelmingly, receiving its heat from the sun itself. Great question.
That's got to be an incredible world with that closeness to.
That's got to be an incredible world with that closeness to its host star, yes. So this planet does not have life on it because it's way too hot, but if there's life on it, it has a really intense sunburn, right? Because it's so dang hot. So that side's 2,000, that side is still 1,500 degrees Fahrenheit. So still super hot, even on the relatively cool night side.
It's a dry heat.
It's a dry heat. No, it has water in its atmosphere. So this is not like Phoenix. And Phoenix is still pretty bad in the summertime.
What do you find most rewarding about being a scientist?
What do I find most rewarding about being a scientist? Getting paid to tell bad jokes to you guys on a random weekday night. Honestly, working for NASA, if you can tell by the shirt again, it's been my dream job. It's been my dream to be working on missions. I count myself extremely lucky that I get to earn a living by studying exoplanets. So I'm really, really very happy and very cognizant and just really blessed, I guess, that I am able to be doing what I love to do. So thank you for paying your taxes, everyone. Yes, thank you. Applaud yourself for paying your taxes. Thank you. And I'll be up here if you have any other questions. Thank you, guys. Appreciate it.
Did you say about the cup of water? You were saying something about the cup of water.
Yeah, so if you took the entire universe and shrunk it to the size of the Earth's oceans, we've only discovered or explored the equivalent of a cup of water's worth. So while we think we know a lot about the universe, there's still a lot more to explore.
Thank you so
Yeah.
much.
I didn't want to ask this in public, but
But while the video cameras are running, that's totally fine. No, I'm kidding. Go ahead.
how can a planet make its sun wobble? You would think, can Earth make our sun wobble?
Yeah, so how can the sun make a planet wobble? Yeah, because of gravitational interaction. So the Earth is causing the star to wobble, but it's a very small amount, yes. So because the bigger the planet, the bigger the wobble, the closer to the planet, the shorter the period of the wobble. So that's why we're finding mostly Jupiter-sized planets, much more massive. When they tug on the star, it's about a meter a second. So you can actually detect wobble on the order of like a brisk walk. But if we wanted to look for the wobble of an Earth-sized planet, it's more like centimeters a second.
Yeah.
So like a nice leisurely pace,
Yeah.
which is hard to find. Exactly. So that's why you need a large telescope. That's why you need very stable technology to do so.
They're the only ones that can pick up the wobble. So, anyway,
Yeah, that's a
good.
great question. You could have asked that.
Good talk, man.
Thanks, man. Appreciate it.
I
Yeah.
have a non-technical question.
Okay.
In your studies in the past, have you ever encountered a person in your field named Robert Williams? Does Williams sound from Berkeley?
I don't know. That's a great
UC
question.
Berkeley.
I'm horrible at names, so I'm probably not the right person to be asking that question.
Well, I mean, I just wondered, in your background, have you ever encountered that? You don't remember encountering it.
No, I don't. Sorry.
All right, that's okay.
No worries.
Okay.
Nice meeting you. Thank you so much for coming. Appreciate it.
Hey, thank you. I've been to JPL.
Crud.
That's why I'm here, because that sparked all kinds of interest. So my field is social science,
Oh, nice. Cool.
not this, but I love listening and hearing about it.
Well, thank you so much for coming. Appreciate
Thank you.
it. Hey, man, how's it going? Hey, Rob. Nice to meet you.
I just wanted to ask, so with current events, have you guys been having any trouble with SpaceX's Starlink when it comes to observations?
Luckily, I have not run into any issues with Starlink at all. I know other people that take very long exposures do. So as all those satellites cross the field, they make those really bad streaks. But luckily, all my exposures are very short comparatively, so I don't have to worry about it. But if you want to take long exposures of the order of long seconds or minutes, then yeah, it'll mess up your observations. But luckily, I haven't had to deal with that.
I guess generally, how long are the exposures whenever you make these observations for transits and stuff?
So for me, it's over the total of a course of hours, but each individual exposure is in the order of seconds. and it depends on the brightness of the star. If the star is really bright, then I can take a shorter exposure. If the star is comparatively dim, then it's roughly on the order of about a minute or so.
So does that mean most of these planets have very small orbit, or very fast orbits, I should say?
Yeah, mostly on the order of days. These planets orbit around their stars.
And that's mostly probably the ones with planets too hot for life.
Yeah, likely they're all too hot for habitable life, yeah.
So TRAPPIST is slower, or has slower transits?
TRAPPIST is orbiting a small star that's cooler.
Okay.
And since it's like if you're in the desert at night, right, if you make a small campfire, you have to be really close to stay really warm. Make a giant bonfire, you have to stay farther away. Same thing with stars, right?
Right.
So TRAPPIST star is about 10 to 100 times smaller than our own sun. So the planets can be closer to their star and still have day orbits, but still be in the habitable zone of their star.
Oh, that's cool. There's one thing I don't know, it wasn't mentioned in there, but do exoplanet astronomers still use, I don't know the term for it, but what is it? It's like, it's not stratification, but like densification or something like that theory. Like, so with the formation of our solar system, it looks like the condensation temperature of different elements corresponds with each planet's orbit.
Exactly. Yeah. So by looking at the different molecules that are in a planet's atmosphere, you can infer where it formed and how the entire solar system formed. So that's the big mystery with hot Jupiters. These large Jupiter-like objects that have things that associate and condense farther out in their solar system, yet they're orbiting very close to their star.
Yeah.
So one theory is that they form far out and they migrate in, and now they're orbiting their stars
because
much
that's
later.
very counterintuitive.
Exactly. Because a lot of these hot Jupiters, their atmospheres are actually blown away by their star because they're so close.
Almost like Venus. Almost, right? Venus is losing its atmosphere.
Yeah, a little bit. And then also just has a very thick atmosphere. I forget if it has a magnetic field or not that it helps. I think it might do. I forget.
Really cool.
Yeah, cool. Great questions, man. Yeah, thanks for coming.
For the amateur astronomy things you were mentioning at the beginning, do you have resource material for that, or just a website?
Yeah, just send me an email and just say, hey, I'm Joseph, and I'll send you the links to our website and also the software you can download as well.
All right. Thank you very much
Cool.
again.
Thanks, man.
I don't quite understand that graph. It's a question of when you see the hot side and cold side of the planet. It seemed to me that it should be symmetric between
Yeah, the hot spot is shifted, right?
Yeah, but what is this one on the left and the right? Is that expanding the upper?
Yes.
Okay, now I understand.
And the reason it's not symmetric is because if we have that planet orbiting around the star, we have that side that's always facing the star. So all that heat goes here at this point. Remember those winds, though? Those winds push the hot spot downwind.
Can't talk, I'm in a conference. Bye.
So it takes all that heat and it actually pushes it downwind and it shifts that hot spot there. So that's why that hot spot is shifted. No, exactly.
I have a PhD in physics.
Oh, nice, yeah. So you know exactly why.
Back from 1957.
Oh, nice. Cool, thanks. Yeah, absolutely great question.
I got involved in the space program before Sputnik. I worked on nuclear rocket engines.
Oh, nice.
Yes,
very cool.
When I interviewed with Los Alamos in 1956, and they said, we have 3 years to build a flyable nuclear rocket engine. And indeed, we did build it, but we never flew it.
Yeah.
Well, thank you very much.
No worries. Thank you so much for coming. Appreciate it.
Oh,